It's all right. I think you have to put in negative 36 first and then do the square root.
Yeah, I don't have a problem with that. So
Yeah.
how do I put in a negative?
Yeah, so same thing after class. If you don't have the calculator you're supposed to have for this class, I can help you, but let's do it outside of class. Okay? Okay. Domain error. So what's wrong? What's going on here? Why is there a problem?
There's no two numbers there.
Yeah, because what is this saying? This is saying to us, what number when you square it do you get negative 36, right? But we know that anytime you have a number and you square it, it has to be positive, right? A positive times a positive would be positive, and a negative times a negative would also be positive. So this isn't possible, is it? So in mathematics, whenever we have square roots of negative numbers, we have to introduce this thing called the imaginary number I, right? We are not going to do any of this, all right? We're not going to touch the imaginary number at all right? And the reason why we're not going to touch it is because the imaginary number system is very near and dear to me. I did most of my graduate research in the complex number system. And all we ever do in an algebra class is just kind of like open the window, let you peek in for just a second, then we close it and we don't ever go back to it. And so I don't think this is even fair to even start talking about it, but here's what I will say. The word imaginary makes you think that mathematicians are just kind of making this shit up, right? Just kind of like, yeah, we'll just come up with this imaginary thing, right? Yeah, it's not real, it just seems very... And when it was first introduced, this idea, most mathematicians looked at the guy who came up with it and was like, yeah, he's a little out there, okay? This is kind of like voodoo math. But it turns out that the imaginary number system is just as real as the numbers you deal with in your everyday life. The best way I can make this analogy is this. So my daughter has a fish tank, right? And we struggle to keep her fish alive. But she's got these fish in here, right? These are them. I think she's down to 6. But anyway, there they are, right? So she's got this fish tank. And do you think these fish have any idea what a car is? Do you think they know what a dog is? You know what I'm saying? Like, these fish are confined to their universe, right? Their universe is that tank. Anything outside of that tank, they have no concept of, right? Would you agree with that kind of idea? Okay, so what I'm trying to get you to see here, or believe, is that all the mathematics that you are ever going to do in your life, because nobody in here is a math major, no one here is an engineering major, all of the math that you ever do, we are keeping you in the fish tank, okay? You're going to stay in that fish tank for the rest of your life, and that's the only math you're ever going to know. But you need to understand that there is a larger system of mathematics that lives, that this system lives within. And in that larger system are the imaginary numbers are in there. But they're just as real as the dog is. You know, if these fish are here and you go try to explain to them what a dog is, they're going to be like, you know what I'm saying? That's the same thing. It got a bad name because in the beginning people didn't believe that it could be useful in mathematics. But after a while it was shown, look, it's very useful. Last little thing on this, and then I promise, it's hard for me not to talk about it because I want you to believe that there's something to it. It's not the little fake guy on your shoulder that you ask advice for, you know, the good and the bad. It's not that, okay? So my brother went to Georgia Tech, he went to Boston University undergraduate. And he was an electrical engineering major. And he called me up with the problem that he and his classmates had been working on for a while, and they couldn't figure it out. And the problem was the mathematics they were using, they were all still in this fishbowl. They had no idea how you could use imaginary numbers to do it's kind of like you take off the goggles here, and then you put on these goggles, and then everything else looks different. And so what I did was I took his problem that he had here, but I worked with it in this number system, got the answer and then converted it back into his and had the answer with, I mean, it was a trivial problem. It took me like 2 minutes, 3 minutes to do. So he was like, what'd you do? And I told him, well, it was this. And even engineers don't get too heavy into the imaginaries, but mathematicians do. So if you're gonna take anything away from this, all I want you to realize is that we won't touch this because we're gonna stay in the fishbowl. But please believe that there's dogs and people and stuff that live outside the fishbowl, all right? Okay, let's move on. For us, if we ever see this as an answer to a problem, we are going to say no solution, all right? If we ever get x is equal to the square root of negative anything, negative 5, we will say no solution, right? All right, we are setting ourselves up here for something, and that is solving quadratic equations. So let me preface this with something. So our goal right now, and maybe we'll do the goal after we come back from a break. Our goal is going to be to solve quadratic equations. And all quadratic equations look like this. We want to be able to solve these. Some specific examples of quadratic equations, I'm going to give you a couple here. 2x squared minus 3x plus 1 equals 0. Is that a quadratic equation? I should say here A, B, and C are numbers, okay? So as long as we see numbers in front of x squared, x, and a number by itself, then we have a quadratic. We also have that A can't be 0, all right? So we cannot have that the number out here be 0, because if this is 0, then this is gone, and it's no longer quadratic. Quadratic comes from the idea that the variable is squared. All right, so that's an example of a quadratic. Is this an example of a quadratic?
No.
So the only condition we have is that we have 3 numbers and the A can't be 0. Could the C be 0? According to this, C could be 0. So it's okay to not have a number out here at all. That's still a quadratic equation. All right, so this is quadratic. It has 3 terms, right? This is a quadratic, but it only has 2. How about this one? Is that a quadratic equation?
No.
So this one had x squared, an x term, and a number by itself, right? Okay, so that satisfies that. This one had x squared and x, but it was missing the number by itself, but that was still quadratic. This one has x squared, a number by itself, but does it have an x term? It does not have an x term, right? But to be a quadratic, the only condition we have is that the A can't be 0. So this is also a quadratic. Let me list out a different way. For this one, what would A be, what would B be, and what would C be for that first problem? For this problem right here, what's A? 2, just the 2. It's the number in front of x squared. What's the B? What's the number in front of x? Negative 3. And then what's C? What's the number that's by itself? 1. Okay? For this one, what's A? 2. What's B? Negative 3. And what's C here? 0, because there is no C, right? It's like there's a plus 0. It's not there. Okay, for the next one, what's A? 2. What's B? 0. See, if there were a 0 here, it would kill this off, wouldn't it? And then what's C? Negative 1, right? These are all quadratic equations. All of these are quadratic equations. And I could list more, but our goal for the rest of the class will be to solve those. So let's take a break, and we'll come back and decide how we're going to solve these quadratic equations. Let's see, it's Why don't we go? Y'all just want to go to 12:30? 12:13, 12, that gives you like 16, 17 minutes? All right, let's go till 12:30. We'll take a break. Yes?